3.5, work and power. So let's do a review question. The woman lifts the 20 kilograms weights, a height of 2 meters. So she lifts these up 2 meters. How much potential energy do the weights gain when they are lifted? Okay, so we want potential energy, the change in potential energy. So that's what we don't know. Okay. So we know that mass is 20. Gravity is about 10 on Earth. Acceleration due to gravity. Change in height is 2 meters. So this is 20 times 10 times 2. That's about 400 joules. So the weights gain 400 joules when she lifts them up. So that's how much work the woman does to the weights. The weights gain that much energy. The woman spends that much energy. So thinking problem. So here we have a man who can lift weights.
When it comes to training for muscle,
we can lift them quickly or slowly. So for example, here we have fast.
greater time under tension, simply meaning that your muscle is
slow
under
and
strain
fast.
for a longer period of time throughout the
here's
set.
slow,
And simple is
and
that
then
you can
here's fast.
perform more reps or
Fast.
use a heavier weight than you can with a slower tempo throughout
Slow.
the set. And since a
Fast and slow. Does the man do more work when he lifts the weights quickly, so fast, at 0.5 meters in 1 second, or slowly at 0.5 meters in 4 seconds? Well, we know the work here is the change in energy. That's energy. And that's mg delta h. The mass is the same. Is your same weights. G is the same. And the height are the same. So the work done is the same in both cases. It doesn't matter whether the man lifts them fast or slow. He does the same amount of work. However, when he lifts them quickly, he uses more power. Slow, less power. Power is work over a change in time. Okay. A change in time. Or the amount of energy used over a change in time. Okay, so that's the formula for power. Power is how quickly we do work or use energy. Okay. For example, while lifting weights, a student does 40 joules of work in 5 seconds. How much power does she use? So we don't know power. We know work done is 40 joules. The change in time is 5 seconds. That's how much time it takes. Then power is work over change in time. Whoops. Which is 40 joules over 5 seconds. That's 8 joules per second. Yep. Another way of writing joules per second, well, 8 joules per second is really 8 watts. So a joules per second, we can use the unit watt. Example 2. A 40 watts light bulb is turned on for 1 minute, which is 60 seconds. How much energy does it use? So power is work over time. One way of thinking about it, while power is 40, time is 60, and we want work. So 40 is equal to work over 60 seconds. We can multiply both sides by 60 seconds, and we get 2400 equals W. So it uses 2400 joules of energy. Okay. Another way of thinking about it is if we look at how much energy used per second, or we can look at, given this much time, how much energy does it use? After 1 second, it uses 40 joules because that's 40 watts. After 2 seconds, that's 80 joules. After 3 seconds, that's 120 joules. So after 60 seconds, that has to be 40 times 60 joules, which is 2400. Okay. Finally, a student lifts books 6 kilograms, a height of 0.5 meters in 2 seconds. How much power does the student use? So we know that work is the change in potential energy, which in this case is mg h. M is 6, g is 10, height is 0.5. So work is 6 times 10 times 0.5. That's 30 joules. Power is work divided by change in time. Work we know is 30. Time is 2 seconds. So the power must be 30 divided by 2, which is 15 watts. So we know it's 15 watts.